In a gear motor, a mechanical gear reduction assembly is attached directly to the output shaft of an AC motor. This assembly greatly increases the torque output of the motor while slowing down the speed by the same percentage that torque is increased. Usually, there are two discrete housings, one for the motor and one for the gear reducer. The gear reduction housing includes gears, shafts, bearings, couplings, and means of lubrication. Spur or helical gears are used where the output shaft is parallel to the input shaft. Bevel or worm gears are used where the output shaft is perpendicular to the input shaft. Customers purchase gear motors where the effort to design and build a custom gear assembly for their high torque application is large compared to the cost of buying a gear motor. This is common when their machine is large and expensive and they only need to buy one gear motor. 1,000-to-1 gear ratios are common in gear motors. This means that the torque output of the gear assembly is 1,000 times as large as that of the motor. The speed of the output shaft is only 1/1000th of the speed of the motor shaft. Gear motors are popular in large mechanical lifts, medical equipment, and power jacks. They operate on either three-phase or single-phase AC power, depending on the design of the motor itself. A universal motor gets its name from the fact that it can be tailored to operate under both DC and AC power. The basic design is similar to a typical DC motor, and minor modifications are needed to run it on AC power. The field coils are analogous to a stator in an AC induction motor, and the armature is analogous to the rotor. The commutator reverses current in the field coils and armature per the AC line frequency. The direction of torque applied to the armature is independent of voltage polarity, determined only by the commutator and polarity of the field coils. We'll get more into how this works when we discuss DC motors. As shown in the diagram on the right, the two-pole field coil is made of tightly pressed laminations overlaid on two coils, creating both field poles of the motor. The armature, shown as the rotor in the diagram, consists of a lamination overlaid on rotor windings, the entire assembly pressed on the motor shaft. The commutator is also pressed on the shaft. The brushes contact the commutator, supplying current to the armature. The graph compares the torque speed curve of universal motors against other AC and DC motors. Universal motors operate at much higher speeds than all other motors. Your application demands speeds above 4,000 RPM, you're likely to specify a universal motor. Universal motors have high starting torque. Coupled with the fact that they're lightweight and small, they are the motor of choice in many consumer products. You find them in portable drills, power saws, vacuum cleaners, food processors, and lightweight portable fans. We will demonstrate their use in a desktop fan shortly. Universal motors have some drawbacks that you need to be aware of. The commutator makes the universal motor noisy, one reason why the previously mentioned products make a lot of noise. They also emit a lot of EMI noise and they can throw off the performance of any nearby electronics design. Some companies use power drills as a quick and dirty way to test the EMI susceptibility of their prototype electronic products. In addition, universal motors are not for continuous use, as evidenced in the type of products they're found in. The commutator brushes wear quickly, and consumers are certainly not interested in getting their hands dirty changing carbon brushes.
Hello everybody. You're staring at a 3-speed electric fan that I bought for $10 in a secondhand store. The fan is blowing air in my face, so I'm gonna have to make this quick before we start ripping it apart. I wanted to at least let you see what it's like. It's rattling around. You may hear that in the distance. You'd ask me, what in the world did you buy a cheap fan for $10 in a secondhand store? It kind of goes like this. We're gonna rip this thing apart. And I have some much better fans in my house that are in much better condition, and I didn't want to destroy those. My wife would not have been too thrilled with me for that. So I bought this fan, and what we're going to do is turn it off in a minute, and then we're going to pull out the electric motor, and you're going to see a very good example of a universal motor being used for a fan.
Well, you can see the base of the fan in this view. There's my price. I think I said $10. It's actually $9.99 on the red sticker. And then you've got 4 buttons that look like piano keys, circa 1980 design or so. If you hit the white button, the fan goes off. If you hit the light gray button, you get the lowest speed, which is what I had it on before. The medium gray button, you get medium speed, and if you hit the black button, you get the highest speed. So that's kind of how people design these buttons and controls back in 1980 or so. In this view, we're staring at the grate that covers the fan, and you can see the trademark. It says Cool Flow. And this is a heavy-duty metal grate in a nice shiny silver color. Behind the grate, you see the fans. Those are the curved black surfaces. We'll get a top view going here in a moment, and we'll show you the actual motor in the back. This is a top view of the fan. The black curved surface on the bottom with all the dust on it is actually the fan blade. There's a black plastic cylindrical cover with a little bite taken out of it on the left side. That's a cover for the rotating shaft. Little silver covered shaft is in there. That's coming out of the white shroud from the back that houses the motor. And then we'll get a view of the back in a moment here. This is the back cover I was talking about. It's got holes in that white plastic cover to prevent the heat buildup from the motor. And that cover is just held down by that one Phillips head screw. And we'll undo that screw shortly, and then we'll get a good view of the inside of the motor. Here's what the fan looked like after I tore it completely apart. There you can see the grating, the upper left corner. Nice steel cover. There's our plastic base. There's our white plastic motor cover. Now you see what the fan blade looks like. Nice black plastic. And then there's our piano buttons. And it looks like the electronics in there is also circa 1980. Something for a museum. Here's a close-up of what the motor assembly looks like with the cable. And there's our screws. We then have another cover here on the left and some other plastic parts whose origins are unknown. And I was thinking for this course about having an extra credit problem about seeing who can explain and write an essay about how to put all these parts back together again. But there's a little problem. I don't know how to grade this essay because I don't know how to get this fan back together again. But the key issue is we're going to take apart this motor housing some more. And for now, we'll just peer inside. You can see the copper windings. It's your basic stator. I'm rotating the armature there now with my left hand. So you can see how the armature rotates within the stator. And then on top of that, after we get a little farther along here, we'll take the back cover off. You can peer in the back now, and that's the back parts. You've also got the copper windings going all the way to the back. And those were some mechanical parts in the back which allowed the fan to rotate, oscillate as it's called, back and forth. Now we've gotten the cover off the motor, and we can show you the front of the motor. Now I'm taking the shaft and rotating the armature. You get a nice view, of course, of all the windings around the armature. Right down here at the base, there's actually peering through as a series of brushes, but the brushes are actually best understood if we take the motor and go to the back. Because once we get to the back, what I can do now is push the stator out, or push the rotor out, I should say, and get you a nice view with the camera into the interior where you are staring at the carbon brushes. And I'm going to point that out and highlight it right here, where you can actually hear me scraping my screwdriver on the brush. Is the rectangular piece for the brush. There's about 24 of them in a circle, and each of those brushes is used to conduct current to the armature. If I pull the armature back, now you get a real nice view. And I rotate the armature and you can see just how close this armature really is to those carbon brushes as it rotates around. I think I said before you got to have about 20 thousandths clearance max. This one probably has about 1 or 2 thousandths clearance because I can feel the armature dragging on the brush as it rotates, and I can actually hear a sound of it. Maybe you can hear it too in this video as it rotates on the brush. So that ends up our tour of our universal motor. I hope you enjoyed this teardown, and we'll do another one a little later in this course for you.